previous slides, some Lewis-Dot structures can have more than one structure, and these were called resonance structures. But are all these resonance structures stable? To determine the stability of these resonance structures, we calculate formal charges. The formal charges are the difference between valence electrons in a given atom and the number of electrons assigned to the atom in the Lewis-Dot structure. The general formula is formal charge is equal to the valence electron minus the lone electrons or the non-bonded electron minus the bonded electrons divided by 2. Charge is Q, that's the symbol for it, is equal to V, the valence electron, minus the non-bonded minus the bonded electron. When we drew the Lewis-Dot structure for bromine, bromine looked something like this. A single bond, and each of the bromines had 6 lone pairs. So how do I use this formula? So if I look at bromine off the periodic table, bromine itself has 7 valence electrons. Now we're going to look for the lone electrons or non-bonded pairs. So if I look at the bromine on the left, it has 6 lone electrons or 3 pairs of electrons that are by themselves. So this is going to be 6 electrons minus the bonded. The bonded is right here. They only share a single bond, so that's going to be 2 electrons because a single bond contains 2 electrons divided by 2, so this is 0. So the formal charge of the bromine on the left is 0, and since the bromine on the right looks the same, it also has a formal charge of 0. So for bromine, this is the most stable Lewis-Dot structure possible for bromine. The stability of the structure is always the lowest formal charge. So the lower the formal charge, the higher the stability. If the formal charge is not 0, you want the negative charge to be on the atom with the higher electronegativity value, and you want the positive charge to be on the atom with the lower electronegativity value. So we're going to find the formal charge of both nitrogen and carbon. So nitrogen has 5 valence electrons. It has 2 lone electrons, or the 2 non-bonded electrons, minus 3 bonds, so it has 6 electrons divided by 2. So if I do my math, the charge of nitrogen is 0. Formal charge of carbon. Carbon has 4 valence electrons. It has 2 lone electrons right here, 2 lone electrons, and its bonded is the same because they share. So it's 6 divided by 2, which is, this is minus 1. The charge of carbon is minus 1. So if I write my charges down, so the formal charge of nitrogen is 0, the formal charge of carbon is negative 1. For the second example, find the formal charge for both of the carbons. So the charge of Q1 is going to be 4 valence electrons for carbon. It has no lone electrons, so that's equal to 0. It has 8 bonded electrons divided by 2. It's 8 because we have 1, 2, 3, 4 bonds because it fulfills the octet rule. Since it's all bonded, there are 8 electrons. So this becomes 0. So the charge of this carbon right here is 0. So if I do the carbon of 2, it still has 4 valence electrons. It has 2 lone electrons right here, 2 lone electrons. And then if I look around carbon itself, it has 6 electrons because it has 3 bond pairs. So 6 electrons divided by 2, this is going to equal to negative 1. So the charge of this carbon is going to be negative 1. Pause the video, find all the charges for each of the carbons, and then check your answer. The formula is Q, formal charge, is equal to valence electron minus the lone electrons or non-bonded electron minus the bonded electrons divided by 2. So the Q of 1 is going to equal to, it has 4 valence electrons, it has no lone electrons, and it has 8 bonded. So that's going to be minus 8 divided by 2. So that's going to have a charge of 0. Charge of the second carbon is going to be 4 valence electron. There's no lone if I look here. Again, it has 4 bonds, so it has 8 electrons divided by 2, so its charge is 0. The charge of the third 4 valence electron, since it was not completely fulfilled, we need to put 2 lone pairs here. We need to put a pair of electrons here. So that means there are 2 lone electrons minus, there are 3 bonds here. So that's 6 electrons divided by 2, which equals a minus 1. The first carbon has a 0 charge. The second carbon has a 0 charge, and the last carbon has a negative 1 charge. So on the right, we have Q of 1. It is, again, carbon has 4 valence electron. The top one has 2 lone pairs. Top one has 1 lone pair, which is 2 non-bonding electron. It has 6 electrons from its bond, because if I count here, there are 3 bonds divided by 2. Charge is minus 1. The second carbon, again, has 4 valence electron. It has no lone electrons because all the electrons are bonded, minus 8 bonded electrons because it has 4 bonds divided by 2. This is 0. This one has a charge of minus, this one has a charge of 0. Pause the video. Draw the Lewis dot structure for CO2. If there are resonance structures possible, please draw them and then determine the formal charges. Carbon is 4 valence electrons plus 2 oxygen, which has 6, which has 16 electrons. The least electronegative goes in the middle, so it's going to be symmetrical. We're going to have a carbon and oxygen on opposite side. Each oxygen has 2 electrons, so it needs 6 more to fulfill the octet rule. Carbon has 2 bonded, so it needs 2 more lone pairs to fulfill the octet rule. So if I count here, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I know this structure is incorrect. My Lewis dot structure had 20 electrons. I have a total of 16 valence electrons, so I exceeded by 4 electrons. Each bond has 2 electrons, so that means I need 2 extra bonds. I'm going to distribute my bonds equally. I'm going to make each one a double, so I'm going to give each oxygen an extra bond. If I do that, there are 4 electrons from the bonded pair, so each of the oxygens need 4 more. Carbon has a full octet because it already has 4 bonded pairs. So I'm going to count to see if our electrons match. So we have 2, 4, 6, 8, 10, 12, 14, 16. So this is a possible structure for CO2. Since we have a double-double bond, we could also have a triple single bond or a single triple bond. I'm going to start the triple on the left side. If I do that, the oxygen on the right side can only have a single bond. Since the oxygen on the left has 3 bonds, that is 6 electrons, it only needs a pair of lones, which is 2 electrons, fulfill the octet. The carbon also has fulfilled the octet because it has 4 bonds, which is 8 electrons. The oxygen on the right has 1 bond, so it's 2 electrons, so it needs 6 more. And if I count my electrons, I have 8. If I count my total electrons, I have 16. So that means I could shift my triple onto the opposite oxygen, and the structure will look similar, but it'll be just flipped. So all these structures possible. So now we're going to find the formal charge. So formal charge Q is equal to V, valence electron, minus the non-bonded electron minus the bonded electrons divided by 2. So the oxygen, I only need to do it once because it's symmetrical. It looks the same. So oxygen has 6 valence electron. It has 4 non-bonded electrons. It has 2 bonds, which is 4 electrons divided by 2, which equals to 0. So the carbon has 4 valence electron. It has no non-bonded, so because there's no lone pairs, and it's completely bonded, so that's 8 electrons divided by 2, so this is 0. Charges, or my formal charges, are 0, which is the most stable structure. I'm going to do the oxygen with the triple bond. If I find the oxygen with the triple bond, it has 6 valence minus 2 non-bonded pair right here, and then it's going to have 3 bonds, or 6 electrons divided by 2, which is plus 1. The carbon is going to be 4 valence electrons minus 0 non-bonded minus 8 electrons divided by 2, that is bonded because it has 4 bonds. This is going to equal to 0. And then the oxygen with 1 bond is going to have 6 valence electrons. It has 1, 2, 3 lone pairs, which is 6 electrons minus 1 bond, which is 2 electrons divided by 2. So this is going to be a negative 1. This one's going to be a plus 1, 0, minus 1. Here is the same, just flipped, so it's going to be minus 1, 0, plus 1. This is why the top one is the most stable Lewis stat structure, because the formal charges are 0. The other two, the formal charges are higher than 0, and you want the negative to go to the more electronegative atom and the positive to go to the least electronegative atom. Oxygen has the same electronegativity value, but they still get both of the charges. One's positive and one's negative. So these last two are not that stable and won't be found. It's the top one. Pause the video, try this problem on your own, and then check your answer. There are 2 nitrogen. Each nitrogen has 5 valence electron. The oxygen has 6, total of 16 electron. Least electronegative goes in the middle, which is nitrogen. So I'm going to start with a single bond for both. Each nitrogen needs 6 more electron because it only has 1 bond. It needs to fulfill the octet rule. The oxygen also has 1 bond, which is 2 electrons, so it needs 6 extra electrons to fulfill the octet rule. The nitrogen in the middle has 2 bonds, which is 4 electrons, so it needs 2 more lone pairs, so it needs 2 pairs of electrons, or 4 electrons. So now we count. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this structure is not correct. 20 electrons, which is from the Lewis dot structure of all single bonds, minus 16 electrons, gives you 4 electrons. Each bond has 2 electrons, so this one has 2 extra bonds. So we're going to, again, start with NNO. I'm going to give 1 to each of the oxygens. I'm going to start with double bonds for both because each of them gets 1 extra bond here. So now the nitrogen on the left side has 2 bonds or 4 electrons, so it needs 4 more electrons or 2 pairs. The oxygen also has 2 bonds, so it can have 4 more electrons to fulfill the octet rule. The central atom already has 4 bonds, and 4 bonds have 8 electrons, so it already fulfills the octet rule. Now we're going to count. There's 2, 4, 6, 8, 10, 12, 14, 16. So this structure is possible. This structure is correct. Since there's a double-double bond, we could also have a triple-single and a single-triple. So I'm going to start with the nitrogen having a triple and an oxygen with a single. So the nitrogen on the left has 3 bonds or 6 electrons. It needs 2 more electrons to fulfill the octet rule. The oxygen has 1 bond or 2 electrons, so it needs 6 more or 3 pairs to fulfill the octet rule. Nitrogen has, the central nitrogen already has 4 bonds, so it already fulfilled the octet rule. It has 8. Now we're going to switch to a single triple bond. Now the nitrogen on the left has only a single bond, 2 electrons, so it needs 6 more electrons to fulfill the octet rule. The oxygen on the right has 3 bonds or 6 electrons, so it only needs 2 more electrons to fulfill the octet rule. The central atom has 4 bonds, so it already fulfills the octet rule. So these are the 3 possible resonance structure for N2O. But are all of these resonance structures possible? So what we're going to do is we're going to calculate the formal charge to see which structure is the most stable. General formula for formal charge is Q, symbol for charge, the valence electrons off the periodic table, minus the lone electrons on the Lewis dot structure, minus the bonds, or you could do the bond electrons over 2, which will give you the same thing. The nitrogen on the outside nitrogen has 5 valence electrons, minus it has 4 lones on the Lewis dot structure, so the non-bonding are the lone electrons on that structure. The number of bonds, there's 2, or you could do the number of electrons, which is 4 divided by 2, which is 2. So this gives you a nitrogen charge of -1. Now we do the central one, which is 5 valence electrons. There is no lones because these are both bonded, minus 4. Because we have 4 bonds, which is 8 electrons divided by 2, which is 4. Equals 1. It's a lot easier, instead of doing B over 2, is just count the number of bonds. Now we're going to do oxygen. Oxygen has 6 valence electron. It has 4 non-bonding electrons or lone electron, minus the 2 bonds that it shares with nitrogen. So this charge is 0. Now we're going to do the nitrogen. that has the triple bond. It has 5 valence electrons, minus 2 lone electrons right here, minus 3 bonds, 1, 2, 3, or you could do 6 divided by 2, which is 3. This is 0. The central oxygen has 5 valence electrons, 0 lones, and 4 bonds. So this is plus 1. The oxygen has 6 valence electron. It has 6 lones, and it has 1 bond. So this is going to be a minus 1. And we need to do the last one too, because none of the structures match. So the nitrogen with a single bond, again, it has 5 valence electron. It has 6 lones, 2, 4, 6, minus 1 bond. So this is a minus 2. The central nitrogen has 5 valence, minus 0 lone electrons, minus 4 bonds. So this is going to be a plus 1. The oxygen has 6 valence electrons. There's 2 lones here, minus 3 bonds. So this is going to be a plus 1. So now I'm going to write all the charges in to compare. So this oxygen is a minus. The nitrogen on the left for this top structure, the nitrogen on the left is a negative 1 charge. The central is a plus 1, and oxygen is 0. For the middle structure, nitrogen has a 0 on the left. The middle one is a plus 1 charge. The oxygen is a minus 1. And on the bottom, the nitrogen on the left side is a minus 2. The nitrogen is a plus, and the oxygen is a plus. 2 things determine the stability of a Lewis-style structure. 1, the formal charges need to be closest to 0 as possible. If they are not 0, the more electronegative element gets the negative charge. The least electronegative element gets the positive charge. So already we can eliminate the bottom one because oxygen is more electronegative and it is a positive, while nitrogen is a minus 2. So if I look at the top one and the middle one, the best structure is going to be the middle one, because nitrogen is least electronegative, is 0 and positive, versus the top one, the outside nitrogen, is a negative charge. In addition, the oxygen on the top one is 0 charge, even though it is more electronegative than either one of the nitrogens. But on the bottom one, it is negative in charge. So this middle structure is the best structure for N2O. Draw the Lewis-style structure, calculate the formal charges and any possible resonance structure for the sulfate ion, and then check your answer. Sulfur has 6 valence electrons. There are 4 oxygens. Each oxygen has 6 valence electrons, and this one has 2 extra valence electrons because it has a charge of -2 equals 32 electrons. Least electronegative is sulfur, and we have 4 oxygens. We're going to all start with a single bond. Each oxygen has 2 electrons, so it needs 6 more. Remember, we want to fulfill the octet rule. So if we count, all the oxygen has 8, fulfill the octet rule. The sulfur also has 8 because it has 4 bonds, so times 2 is 8. And we have 32 electrons. So this structure should be correct. Let's calculate the formal charge. So formal charge, Q is equal to the valence electrons minus the non-bonding minus the bonded electrons over 2, or just count the number of bonds. So for the oxygen, they're all the same. So we have 6 valence electrons. Each of the oxygen has 6 non-bonding electrons or lone electrons minus 1, which is the bond between the oxygen and the sulfur, so this becomes a -1. The sulfur has 6 valence electron minus 0 lone electrons minus 4. This is equal to plus 2. So all the oxygen has a negative, which you want because it is more electronegative. So if the value is not 0, if the formal charge is not equal to 0, you want the more electronegative to get the negative formal charge. Sulfur is a plus 2, which kind of makes sense because sulfur is the lower electronegative value and you want it to be the positive. Is it possible for the sulfate ion to have other Lewis dot structure? Since sulfate ion central atom is sulfur and sulfur is located in period 3, it can exceed the octet rule because it has empty d orbitals. One of the possible bonds for sulfur is a double bond on opposite sides with oxygen surrounding it. All the oxygens with one bond would need additional 6 electrons or 3 lone pairs. The one with the double bonds would need 4 more electrons or 2 lone pairs. And this is a possible structure. So you say, how do I know it has a double bond? We know this structure is possible through experiment. And let's see how stable this structure is. If we calculate the formal charge for the one bond or the single bond, the valence electron for oxygen, there are 6, minus there are 2, 4, 6 lone electrons, minus 1 bond, or you could do 2 electrons divided by 2, and this equals to -1. The double bond oxygen again has 6 valence electron, minus 4 lones because it has 2 and 2 here, minus 2 bonds or 4 electrons divided by 2, which is 2, and this is 0. The sulfur in the middle has 6 valence electrons. It has 0 lone pairs or lone electrons, minus 6 bonds. If I count here, there's 2 bonds here, 3, 4, 5, 6. So this has a charge of 0. Formal charges on the sulfate ion, the double bond oxygens both have a charge of 0. The sulfur has a charge of 0. And the single bond oxygen has a charge of -. If I compare it to the top structure, this bottom structure is more stable. Why? Its formal charges is very close to 0, versus on top, where the formal charges are +2 and -. So the bottom structure is a better structure or a more stable structure than the top structure. Since this structure has a double bond, this will have resonance structure. The double bond could be on the top and the bottom. The double bond could be on the top and to the right. The double bond could be to the right and to the bottom. The double bond can also be from the bottom to the left, or it could be from the left to the top. So these are all possible resonance structures, and we have to put in all the lone pairs. Since these are all resonance structure, they are all separated by double-headed arrows. In addition, these are ions, so we need to put brackets in the charge. That goes for the top one and for the top one above. Sulfur, phosphorus, a lot of times they will exceed the octet rule because of their empty d orbitals. Scientists, before their experiments, knew that sulfur exceeded the octet rule, but they did not know that sulfate ion had 2 double bonds and it was a more stable structure. For this class, if you fulfill the octet rule, I will take the single bond as the correct answer. You do not have to do all of these unless it tells you to draw all the possible resonance structure and find the formal charges. This bottom structure and the structures down here are more stable because their formal charges are closest to 0. The double bond oxygens are 0. The sulfur is 0. The single bonds are negative, and the more electronegative atom will get the negative charge. The top one is not as stable, even though oxygen has the -1 charge when it is the more electronegative atom, and the sulfur is least electronegative and has a 2+ charge. It is not as close to 0 as the bottom structure. So again, for class or in the test, unless it asks for all possible resonance structure with formal charges, if it follows the octet rule and the duet rule, I will take the structure above. However, in college, you need to do the correct ones.